Hello, my dear students. I have come with a new problem today for moment of inertia. So the question here is to determine the moment of inertia of the given L section with respect to its centroidal axis. So as we have already discussed, centroidal axis are nothing but when you draw an x-axis and a y-axis which are passing through the centroid, then it is called as centroidal x-axis or centroidal y-axis. Now to solve this type of problem, the first step is we have to determine the centroid as well as the centroidal axis need to be drawn. Now for this thing, what I'm assuming is let there be a reference x-axis exactly at the bottom of the section. This is reference x-axis, and let there be some reference y-axis. Now I'll assume that there is a point capital C whose coordinates are x bar and y bar. Now here x bar and y bar are the coordinates of centroid for the given L section. And the next thing is we have to divide the given section into two rectangles. Now I'm drawing a line over here which is dividing the entire section into two rectangles, the first rectangle and the second rectangle. Now here let us assume that there is a point C1 whose coordinates are x1 comma y1, and let us assume there is one more point, that is C2, whose coordinates are x2 comma y2. Now C1 x1 y1 are the coordinates of centroid for the first rectangle. C2 x2 y2 are the coordinates of centroid for the second rectangle. And the next step, I'm just writing down the dimensions of the first rectangle. For the first rectangle, the width is 20 millimeter, and the depth of the section from here till here, right, it is 100 millimeter, which is given. And the area of the first rectangle will be 20 multiplied by 100, that is 2000 millimeter square. Now coming back to the second rectangle, right, width B2 will be 80 millimeter. So how is it 80? So the total width of the section is given as 100 millimeter. Now from the 100 millimeter, this 20 millimeter will be gone. The remaining part will be only 80 millimeter. So we have 80 millimeter here, and the depth of the section is 20 millimeter. Next, if I consider A2 as the area of the second rectangle, then A2 will be 80 multiplied by 20, that is equal to 1600 millimeter square. The next step is to find out C1 x1 y1 and C2 x2 y2. C1 x1 refers to the distance from reference y-axis. This particular distance, it will be half of this total width. So that is half of 20 millimeter, so it will be 10 millimeter, and y1 will be half of 100 millimeter, that is 50 millimeters. And for the second rectangle, x2 and y2, C2 x2 and y2, x2 will be the distance from the reference y-axis up to this particular point. Now it can be calculated by adding this 20 millimeter here and half of the width of the second rectangle. So half of width of the second rectangle is 40 millimeter. 40 plus 20, it will be equal to 60. So x2 will be equal to 60 millimeter, and obviously y2 will be half of the depth of the second rectangle, that is equal to 10 millimeters. The next step is to calculate the centroid for the given section. We have the formula capital C x bar y bar, which is equal to sigma ai xi divided by sigma ai, and sigma ai yi divided by sigma ai. So expanding the formula here, x bar, which is equal to sigma ai xi divided by sigma ai. This can be written as a1 x1 plus a2 x2 by a1 plus a2. So I'll write down all the values here. A1 is 2000 multiplied by x1 is 10 plus a2 is 1600 multiplied by x2 is 60 millimeter divided by 2000 plus 1600. Now after substitution and calculation, right, we got x bar, which is equal to 32.22 millimeter. Similarly y bar, which is equal to ai yi divided by sigma ai. So a1 y1 plus a2 y2 by a1 plus a2, that is 2000 multiplied by y1 is 50 plus 1600 multiplied by y2 is 10 divided by 2000 plus 1600. Now here also we'll get y bar, which is equal to 32.22 millimeters. Okay, we got this. Okay, we got the centroid here. Centroid capital C, x bar and y bar, which is equal to 32.22 and again 32.22. X bar is 32.22, y bar is 32.22. Now, when I draw a horizontal line which is passing through the centroid, it will become the centroidal x-axis. I am representing centroidal x-axis as capital XX, and similarly when you draw a vertical line which is passing through the centroid, we can designate this thing as centroidal y-axis. Now, centroidal x-axis and centroidal y-axis. Similarly, for the first rectangle, when you draw a horizontal line which is passing through C1, this can be called as x1 and x1. x1 axis refers to centroidal x-axis for the first rectangle, and we have a vertical axis. You can write this one as y1 and y1. y1 and y1 refers to centroidal y-axis for the first rectangle. Similarly, for the second rectangle, if I draw a horizontal axis which is passing through the centroid C2, that can be designated as x2 and x2, which can be called as centroidal x-axis for the second rectangle. And similarly, when I draw a vertical line which is passing through C2, you can call that one as y2 and y2, which are centroidal x-axis and centroidal y-axis for the divided rectangles 1 and 2. Now here, x1 and y1 are the centroidal x-axis and centroidal y-axis for the first rectangle. Similarly, x2 and y2 are the centroidal x and y axis for the second rectangle. And coming back to capital X and X as well as y and y, those are the centroidal x-axis and y-axis for the entire section. Now, from the parallel axis theorem, we have the formula to calculate the moment of inertia with respect to any of the axes. Moment of inertia with respect to centroidal x-axis, Ixx, is equal to moment of inertia with respect to centroidal x-axis plus area multiplied by square of distance between those two axes. Among these two axes, one of the axes should be centroidal x-axis for the entire section, and the other one should be the centroidal x-axis for the divided rectangle. Now here, as we have two rectangles, I am taking sigma Ixx plus a h y square. Now expanding this one, for the first rectangle it will be Ixx1 plus a1 h y1 square plus Ixx2 plus a2 h y2 square. Now here Ixx1 refers to moment of inertia of the first rectangle with respect to its own centroidal x-axis, and a1 refers to area of the first rectangle. hy1 refers to the distance between the centroidal x-axis capital XX as well as x1. Now this particular distance here, it can be taken as hy1. So why do we need to call that one as hy1? H refers to the distance between the axes, y refers to in which direction you are measuring it, and 1 refers to the first rectangle. It is the distance in between the centroidal x-axis as well as the centroidal axis for the entire section in between these two axes. Now similarly, we can also call hy2 in between these two axes, right? You can see the centroidal x-axis for the entire section as well as centroidal x-axis for the second rectangle. Now distance between these two axes is taken as hy2. Now there is a simple way to calculate hy1 and hy2, right? So hy1 can be written as the difference of y bar and y1. I am calling it as difference. So what is the difference here? y1 is 50 minus y, capital Y is 32.22. Similarly, hy2 is the difference of y bar and y2. So that can be written as, so the bigger one is 32.22 minus 10. These two are the values. Now after substituting and calculating the values, we will get hy1, which is the difference between these two axes. It is equal to 17.78. We got it as 17.78, and hy2, which is equal to 22.22. Now these are the most important things which we require. Next, calculating I capital YY. The solution is not yet completed. Similar to the above formula, I am writing this one as I YY plus A into H X square. So expanding the formula here, as we have two rectangles, I can write this one as I YY for the first rectangle plus A1, area of the first rectangle, HX1 square, plus I YY2 plus A2 multiplied by HX2 square. Now here HX1 and HX1 as well as HX2 are the distances between the centroidal y-axis as well as the centroidal y-axis of the first rectangle. Now this particular distance here, it can be taken as hx1. As you have already known, h is the distance between the axis, x refers to along which direction you are measuring it, and 1 refers to for the first rectangle. It is the distance from the centroidal y-axis to the centroidal y-axis of the first rectangle, hy1. And similarly we have hx1 as well as hx2. This is the hx2. It is the distance from centroidal y-axis to the centroidal y-axis of the second rectangle. So this can be written as 32.22 minus 10. How did we get 32.22 minus 10? So as you have already known, right, it is y bar minus y1. Now it will become difference of x bar and x1. Similarly, we have difference of x bar and x2. This can be written as 60 minus 32.22. The first one will be same thing again, 22.22, and the next one will be 27.78 millimeters. This is 27.78, and over here it is 22.22 millimeters. Now still expanding the formula, Ixx1 refers to moment of inertia of the first rectangle with respect to its centroidal x-axis. So that can be written as b1 d1 cube divided by 12. As we have already calculated this one in the previous class, moment of inertia of any rectangle with respect to its centroidal x-axis will be bd cube divided by 12. And area of the first rectangle will be obviously b1 multiplied by d1, and we have calculated hy1. Right, the value of hy1 is already calculated here, right? Hy1 is y bar minus y1, that is 17.78. So I'm going to write only y bar minus y1, difference of y bar and y1 here. This is for the first rectangle, and for the second rectangle it will be b2 d2 cube divided by 12 plus b2 multiplied by d2 this is square again, right? b2 multiplied by d2 is the a2, and we have difference of y bar and y2 square. Now to substitute these values, right, I'm just writing down all the values over here. So for the first rectangle we have b1 which is equal to 20 millimeter, d1 is 100 millimeter, a1 which is equal to b1 multiplied by d1, that is 2000 millimeter square, and hy1 is the difference between both the axes, that is y bar minus y1, or difference of y bar and y1, that we have already calculated that one as 17.78 millimeter. And next, for the second rectangle we have b2 which is 80 millimeter, d2 which is equal to 20 millimeter, and a2 which is b2 multiplied by d2, that is 1600 millimeter square, and hy2 which is difference of y bar and y2, that is 22.22 millimeters. Now substituting all the values in the formula which is given above, we get Ixx, moment of inertia with respect to centroidal x-axis, which is equal to b1 d1 cube divided by 12 plus area a1 multiplied by hy1 square, and b2 d2 cube divided by 12 plus a2 multiplied by hy2 square. Now we get Ixx, which is equal to, for the first rectangle we get this value, and for the second rectangle we get this value after substitution, and totally moment of inertia of the entire section with respect to centroidal x-axis will be 3142222.24 millimeter to the power 4. The units are most important. If you don't write the units, your entire problem will be wrong. Now next, let us calculate the moment of inertia with respect to centroidal y-axis, Iyy. Already we have written the formula, that is Iyy1 plus a1 hx1 square plus I yy2 for the second rectangle plus a2 multiplied by hx2 square. Now expanding the formula, you can write this one as, so moment of inertia of any rectangle with respect to centroidal y-axis will be d1 b1 cube divided by 12 plus same thing again, b1 multiplied by d1 is the area, and this one will be difference of x bar and x1 square. And for the second rectangle it is d2 b2 cube divided by 12 plus b2 multiplied by d2 multiplied by difference of x bar and x2 square. Now so just let me write down all the values again, right? So already I have written b1 d1 a1 and hy1, b2 d2 a2 as well as hy2. So the only thing which we require here is hx1 and hx2. So hx1 is 22.22, which is already calculated, and hx2 will be equal to 27.78 millimeter. So I'm substituting all the values in here. So we'll get d1, which is equal to 100 multiplied by b1 is 20 cube divided by 12 plus the area of the first rectangle, it is 2000 multiplied by 22.22 square. This is for the first rectangle, plus d2 20 multiplied by 80 cube divided by 12 plus 1600 multiplied by 27.78 square. Now after substitution and calculation, right, we'll get I capital YY. In total I am calculating. So totally we will get 3142222.233 millimeter to the power 4. So as you can see here, we are getting moment of inertia with respect to centroidal x-axis as well as moment of inertia with respect to centroidal y-axis as same. That is just because both the sections are symmetric about a particular axis. Thank you.